Hello everybody, this is Dr. Mears. Today we're going to be reviewing Scatterplot's correlation in the equation of the regression line. I have taught you individual lessons on Scatterplot's correlation in the equation of the regression line, and today I'm hoping just to bring it all together so it'll be a nice review session, and I'm hoping that it won't take too long. So let's go. Example, 12 mothers were asked how many hours per day on average that they held their babies and how many hours per day on average that the baby cried. The results are given in the following table. This is the same data that we used in class. So we have a couple different things, and please note part D says new learning. So you're going to have to make it through the video. Let's get to that new learning. Part A, describe the type of correlation. Now, when you describe the type of correlation, you always, please start with a picture. And because we have quantitative data that's represented in quantities, we need to make a scatter plot. So first, let's define our variables. The baby held and baby cried. So we hold a baby, and hopefully when we hold a baby, it will cry, not as much. That's what I hope when I hold my children. So what we're going to be doing here is we're going to be identifying that the baby held is our X variable. That's our independent. So that is the independent variable where I can control it. I can control how many hours I hold my baby. I can't control, however, the baby cried, which is my dependent variable. I'm hoping I can by holding it. So we're going to make these L1, which is always X, and L2, which is Y. So we have identified our variables, and we also identify what list we're going to do in the calculator. So doing that, we're going to come down here, and the first thing that we're going to do is we're going to do a scatter plot. Then we're going to write our Foxy. Now, when we do a scatter plot, what I've done is I have just did a sketch. So why don't you try right now on your graphing calculator, see if you can type in L1 and L2, put the data in. And so what you're going to be doing is you're going to go Stat, Edit, and make sure your L1 are the average hours a baby is held, and L2 is the average hours the baby cried. And you're going to go to your stat plot. Now here you can just check if it's on, if the scatter plot is selected right here, and if you have L1 and L2. If that's set to go and everything here, these other three are off, then you can simply zoom 9 and it'll bring your scatter plot up. Then you do a little sketch. I don't need a draw here, so I don't need a perfect draw. I just need a sketch. I want to see what it looks like. And as you can see, it has a decreasing trend. So as the average baby hours that you hold a baby increases, hopefully their crying will decrease. So now I'm starting to actually interpret this scatter plot, and that brings us to part 2, which is our Foxy. So let's come over here. When interpreting a scatter plot, what you want to do is, and I'm actually going to do this. I want to go piece by piece. You're going to remember this acronym. This just helps you to make sure you have all of the elements that you need for a good interpretation. So the first sentence that I started with was actually what I looked at in my nice little scatter diagram here. It says, as the average hours a baby is held increases, the average hours a baby cries decreases. So this is going to represent my context. I started with that first. Now remember, you don't have to start with it first, but after I drew it, my mind automatically went to, well, what does the picture look like? So that's my context. Next, after that, I want to describe the actual relationship. What do I see? Because I'm seeing a decrease. Does it look linear? I'm thinking so. It has a nice linear trend, and it's definitely negative because there is that decrease. So let's describe form, direction, and strength. And that's this sentence here. There appears to be a strong negative linear relationship between average hours a baby is held and the average hours a baby cries. Please notice I'm always including the average. Okay, that's one thing to notice. But let's go through and make sure that we have the elements from Foxy. So strong describes strength, negative describes direction, and linear describes form. So I have described 3 different elements for my interpretation. Okay, next. Now, here's the thing. In statistics, when you mention that we have a strong relationship or a negative relationship or a linear relationship, you need some type of number to back this up because this is what we see. So we need to prove this statistically. And that's where the Pearson's product moment correlation coefficient comes into play. And so that is right here. The Pearson's product moment correlation coefficient is negative 0.9595, which is close to -1. Now this -1, there was a sheet that I gave you. It had a nice chart on it and it had a few graphs on it to describe when this number is strong, moderate, weak. So that's where I got this -1 from. This verifies a strong negative linear correlation. So I have now verified my form, direction, and strength. And I also used my word correlation. The reason why I can use this word correlation is because I cited the number. Once I have the number, I can use this. Up here, I just said relationship because I could just describe it what I saw and I knew it was some type of relationship. Now I know that it's an actual linear correlation because I have that number that represents a linear correlation. Okay, so let's recap. I have context, I have direction, strength, form, and I actually verified it. I don't have outliers. In class, I went over 2 different types of outliers. Regression outliers, which are points that are too high or too low. So points maybe, if we go back to our scatter diagram, they're way up here, or maybe even way down here in the corner. And there's also influential outliers, which are way too much to the right. So one might be over here, or way too much to the left, which could be over here. So separated in the y direction are your regression, separated in the x direction are your influential. Now I put down this little pencil test. Sometimes I like to do this when I have a nice little diagram like this. What I do is I just put my pencil on there and I see, because it represents my linear trend. Do I have any points that are way too high or low or left or right? And it doesn't appear so. Now, this is not a statistical test using the pencil by any means, but it's something just to help you young statisticians understand what you do when you start to look for outliers, especially on a scatter plot. So you can you can try this out. Okay, so I don't see any that appear to be either regression or influential. So what I did is I wrote out, there appears to be no apparent outliers as there are no points that lie outside the linear pattern. And so here's my nice little outliers. So I have everything. I have my context. I have my form, direction, strength, and I verified it statistically, and then I have my outliers, which there are none, but I have my outlier sentence. This would be a good place to pause if you did not understand or you want to ask me questions in class because you are hopefully watching this in class. Or if you're not, then you can always send me an email. Let's go on to part B. Part B, this is the same paper. This was our X and our Y, L1, L2. I just needed a new piece because I write really big. So we are on part B. If there is a strong correlation, find the equation of the regression line. So you need to do this in your calculator, equation of the regression line. And when you do, what you did is you had this, and then you had to do a linear regression. Sorry. No. You had to go calc 4, and in order to get your correlation coefficient, your negative 0.9595, this number right here that you used, your Pearson's product moment correlation coefficient, you also found your A and B. And you need those because it gives you the equation of the regression line, which is really nice. So y equals ax plus b. This is your equation of your regression line. Actually, we need our numbers in, but I'm going to explain the equation first. A is going to be your slope, which is your rate of change. B is your y-intercept. It intersects the y-axis, and it's also the value of y when x is 0. Concepts you learned in Algebra 1, which I'm hopefully reteaching you now, maybe even getting from your long-term memory. So in your calculator, you received an A of negative 0.701 out of 3 significant figures and a B of 6.89. So our equation is, moving the paper over, y equals negative 0.701 times x plus 6.89. However, the y and the x here aren't defined. I don't know what they are. This could be an equation for anything. So writing it out statistically, I like to put the words in. So statistically, our y is the average hours that a baby cried, and our x is the average hours that a baby is held. So I can input those words. I also threw a little hat on it, hat on our baby. Baby hats are so cute. This means that it's my prediction line. This means to predict. I'm predicting the baby cried hours because when we go back, this is the true actual data. This is the actual data we gathered. This line is going to help us to predict. It's going to help us to say, hey, you know, when a baby is held for 5 hours, I can tell you how long using this line that the baby's going to be crying on average. So I bet you that's our next question, which let's go up and look. Use the regression equation to predict how many hours a baby would cry if the baby was held for an average of 5 hours. How does this compare to the actual data? So let's use our regression equation. And that is on, we're going to use this equation right here that we received, which is right here. Yay! Just rewrote it over, and I'm going to input 5 because that's the average hours that a baby was held. And in my calculator, I'm just going to do negative 0.701 times 5 plus 6.89. Negative 0.701 times 5 plus 6.89. And I'm going to get 3.385. 3 significant figures is going to be 3.39. So let's see how I wrote that out. I rewrote it out as predicted baby cried is 3.39. If the baby was held on average of 5 hours, then I predict, using my equation, that the baby would cry for an average of 3.39 hours. You know what? I'm going to change one thing because I've been reiterating that you should always put down the true value. So I'm going to put down my true value here. Predicted baby cry, 3.385. Then in my answer, I'm going to go to 3 significant figures. I have both, and it looks better, especially because if you give this answer and you don't round to 3 significant figures correctly, you're going to still get some credit. So here's my nice sentence. You should always put in a complete sentence. I actually told you I predicted using my equation. Now, how does this compare to the actual data? Well, let's look back at the actual data. I'm going to circle 5 hours that a baby is held. It actually cried for 3.5 hours. This is the true data. When I used my prediction equation, I received an answer of 3.385. So predicting 3.385. Well, how far is that off? Let's look. If you take your actual, which was 3.5, and you subtract it from your predicted, 3.385, I receive the difference. Please notice I use the entire number. Difference of 0.115. And this is actually a positive difference because it came out to be a positive number. What does this mean? What would my sentence look like that I wrote? Here we go. The actual time was 0.115 average hours higher than the predicted time. That makes sense. Okay. Sometimes it'll be higher, sometimes it'll be lower, because remember, we're using a line of prediction. Now, I just want to show you one thing, because I keep talking about this line of prediction, and what I'm going to do is I'm actually going to show you on the calculator. It's negative 0.701, and I'm going to be using this xt theta n button right here, right there, as my x, plus 6.89. So what I did is I entered the equation, I pushed y equals, just y equals, and I got to y equals. And now I'm going to press graph. And so here is my data, and here's my equation of my line. My equation of my line intersects the y-axis up here at 6.89. it also passes through the mean of x and the mean of y, which we haven't discussed, but I'm bringing it about right now. So this line intersects my y-axis at 6.89 and also passes through my mean. So if I were to draw this on here, I'll try to do it as best as possible. Whoops. This right here would be 6.89. This is my y-intercept. And it would pass through my mean. Let's just find the mean quickly. We're going to go to Stat Calc. It is two variable statistics. I want to tell my calculator L1, L2. X bar is 4.83 and Y bar is 3.5. So when we go here, we are going to find the point 4.83 and 3.5. X bar, Y bar. My line will always cross through my y-intercept and my mean. This mean, was this a data point from my actual data? No, this was not in my actual data. I found this point in my calculator and I added it in to show you that this line will always pass through there. Okay, I just wanted to give you some background information. Now, if I went to 5, which is probably here, and I would go up, I would find my predicted. So this point right here would probably be my predicted, which would be my 5, 3.385. Yep. So if all of my points from my predicted equation will be on my line, because this line helps you to predict. So there you go. Lastly, let's go to our new learning. Our new learning was about r squared. And it says, new learning, finding r squared. Find r squared and interpret the meaning and context of the problem. R squared is known as the coefficient of determination. This is an indication of how much of the variation in the y values is accounted for by the linear relationship of y on x. What does that look like in context? Let me show you. Here's part D. R squared. And you find r squared again on your calculator when you run your linear regression. You received an A, a B, you received an R. Now there's this R squared. R's is 0.920667151. So what I did is I wrote it down. R squared equals 0.921. I rounded to the three significant figures. You should write the whole number out as well. But what do you do with this number? First, change to a percent. Multiply it by 100, we get 92.1%. What does this mean? This means that 92.1% of the variation in the average hours a baby cries. So the variation, how many average hours a baby cries, that variation is accounted for by the linear relationship of average hours the baby cried on average hours the baby is held. So we can account for 92.1% of how those Y values, or the variation of how long a baby cries on average. That's really good. The closer to 100, the more accountability your linear relationship has. This has been a complete review with a little bit of new learning on scatterplots, correlation, and the equation of the regression line. Please review, revise, ask questions. I hope this helped. Good luck.